welcome back to another video lecture for section 2.3. This is still part of unit 1, but we're kind of skipping around a little bit on the sections. So 2.3 covers functions, and for those of you taking notes, this is going to be one of the more important things that you take notes over because this concept does not go away, and in fact, if you're weak on this concept, it's going to make the rest of your time in college algebra very, very miserable. So make sure that you're taking good notes over this. We'll be going over plenty of examples in class. And just get ready, this is going to be a slightly longer section than the rest of them are. Okay, so what exactly is a function? To define a function, we first have to know what a relation is. And a relation is just any set of ordered pairs. That means we have an input value and we have an output value. So I've written that here in this first kind of bullet point for us. A function, on the other hand, is a special type of relation. So all functions are relations, but not all relations are functions. A function is a special type of relation where for each distinct first component of the ordered pair, that is the x component, there is exactly one value for the second component, or in other words, there's exactly one y value for every x value. Furthermore, we say that a function is one-to-one because for every one input, we get exactly one output. There's no ambiguity. I can't say that the input is Tuesday and the output is both 3 p.m. and 5 p.m. I would need to say that the input is something like Tuesday and the output is 5 p.m. If I only give one time like this, there's one output, then you know exactly what I'm talking about. When it's Tuesday, I'm looking at something happening at 5 p.m. instead of happening at 2 different times. There's no ambiguity there. Furthermore, we know that a function is going to pass what we call the vertical line test, and this is kind of a recall portion from Algebra 2. So if you're unfamiliar with the vertical line test, I do suggest that you go back and do a little additional reading. I'm going to cover this in detail in some of the examples, though, a little bit later. So what we need to know, functions are a special type of relationship where every input has exactly one output, no ambiguity. A function is called one-to-one if it passes our vertical line test. And the vertical line test is effectively what we're using to test to see if a specific graph represents a function or not. There are two really, really big idea concepts in this section. The concept of domain and the concept of range. And these will not go away when we look at intervals of increase and decrease a little bit later into this video. We're going to be looking at it in context of the domain. So the domain is going to be all of the values that x can take. In other words, where is the graph drawn from left to right? So when I'm looking at something from left to right, what numbers are covered on that graph? The range, on the other hand, is all the values that y can take. So when I look at a graph from bottom to top, what are all of the different values that are covered in that respect? So we have a couple of examples of how to determine if something is a function. And the little hint that I want to give you here, the kind of easy way to remember it, is if you're looking at a relation, if you can develop a list of ordered pairs, go ahead and do it. And then what you're checking for in the list of ordered pairs is whether or not the input values repeat themselves. So what I mean by the input values is the x coordinates. That would be these numbers here. These are all x values. Notice that I don't actually really care about what's happening in the y portion. I only care if the x values are repeating themselves with different output values. So we're asked to determine if this relationship M is a function or not. Now, notice that I do call this a relation because M is a set that contains a whole bunch of ordered pairs, which is our definition for what a relation is. So we know M is a relation. We have to determine if it's a function. What I'm going to look for real quick is if the x values repeat themselves. So I have a -4, I have a -3, and I have a +3. All of these are distinct and separate numbers. They do not repeat themselves. And so regardless of what the outputs are, I know that this thing is a function. I'll write that in right here. It is a function because the inputs do not repeat. Now, a little note here, notice that negative 3 comma 1 and positive 3 comma 1 are both ordered pairs in this relation. And furthermore, that the outputs are repeating themselves here. This is going to be something we cover a little bit later into the semester, but for right now, when we're just determining if it's a function, the outputs are allowed to repeat, the inputs are not. So next we want to determine if the relation n is a function or not. We know that this is a relation, again, because our definition says that it is a set of ordered pairs. So I have a set here, and I've got 4 ordered pairs in it. It is a relation. Now, if I'm going to look at just the x values, I'm going to notice that I have a 2, a 3, a 4, and a 5. None of those x values repeat themselves, and so this relationship n is in fact a function. We're asked to determine if the relationship p is a function. I know that p is a relation because it is a set containing 1, 2, 3, 4 ordered pairs by our definition. So again, same sort of thing. I'm going to check to see if the input values, the x coordinates, repeat themselves. I have a -4, a 0, a 2, and a -4. So I've said -4 twice, which means it has repeated itself. I got to do one more thing here and make sure that they are mapped to 2 different values, because if it's just the same value, well then maybe they just wrote the same thing down twice. It would still be a function in that case. But notice that I have -4 going to +3, and then over here I have -4 going to -3. So those are 2 different output values for the same input value. So this thing right here is just a relation. Remember, we know that it is a relation because this is a set containing ordered pairs, but it is not a function because the input numbers repeat themselves with different outputs. So in example 2, I've cleaned up the board here. I want to talk to you about how the vertical line test can help us to identify if something is a function or not, because the first 3 examples really were not, they were very nice in the sense that they actually gave us the ordered pairs, so we could simply just check to see if the inputs were repeating themselves. And the vertical line test is a way to check to see if the inputs are repeating themselves when we've been given a graph. So the way that this works is pretty simple. What you're going to do on Pearson, more than likely, is blow up the graph to where you can see it well, and then you take your pencil and you simply hold it vertically and see if the graph crosses the vertical line, the imaginary vertical line of your pencil in more than one place. So I can actually draw it on my board here. And so what the vertical line test states is if we just draw a sequence of these vertical lines across our graph, and we need to make sure that every vertical line only crosses in one place, and some will be more obvious than others. So usually what's easiest to do with the vertical line test is to check to see if we can find one example where a vertical line that I could draw here is crossed in more than one place. So let's look at A. A, we have this kind of ellipse type figure here. I can go ahead and tell you this is not a function. And one way that we could do this easily without having to draw additional vertical lines is just look at the y-axis. I have 2 distinct places that this is being crossed by my green line. I've got this spot right here, and I've got this spot right here. So because I have crossed this vertical line in 2 distinct places, we have not passed the vertical line test, which we have established makes this thing not a function. It is simply a relation. It is a set of ordered pairs. Now, why is that? Well, notice that this particular component might have an x coordinate of 0 and then a y coordinate of something like -1 or -2. And this component will also have an x coordinate of 0, but it'll have a y component of +1, +2, +3, something like that. So I have one x coordinate, 0, that has repeated itself. And actually this happens in more than one place. If I were to draw any vertical line through this figure, you notice I can do that here, and I will end up with 2 places again that this thing crosses. I can do that over here, and I will have 2 places where this thing crosses. On B, you will notice that no matter what vertical line I draw, I'm not going to be able to get the green line to cross in more than one place. So if I were to draw a vertical line here, and a vertical line here, and a vertical line here, and a vertical line here, this green line will only ever cross it in exactly one place. That's here, that's here, that's here, that's here, and that's here. And so since this has passed our vertical line test, in reality, if I just hold my arm up and move it from left to right, it only ever touches that green line in one place. That tells me that every point on this graph only ever touches it in one place, which is our definition of passing the vertical line test. In other words, for every one input, there is exactly one output, and this thing is a function. So we have not a function, and we have function. For C, we can do the same thing. Notice that it doesn't always even have to be like a smooth graph where I've drawn an entire line. Here I've just got 4 little green dots that represent my relation. And so if I just look at if the input values repeat themselves, this one should be pretty obvious because at -2 I have a dot above and a dot below. It's obvious that the input value has repeated itself. Same thing here too. I have a dot above and a dot below. So it's obvious that the inputs have repeated themselves. And we could go a step further and actually perform our vertical line test here. If I draw a vertical line right here, excuse me. If I draw a vertical line right here, you will notice that both of these dots intercept that vertical line, and so this thing is not a function. Example D, we have a parabola figure like this. This is something that you may be familiar with from the end of Algebra 2. And again, we can test this using the vertical line. Now you gotta be kind of careful with the vertical line test here because notice that this thing does kind of extend forever downwards, but it'll get increasingly straight. So it'll kind of fool you into thinking that this is vertical, but we need to use an element of common sense here when we're doing the vertical line test. This is one reason why we don't just justify something being a function or not simply on the basis of the vertical line test, because some of these functions, they get very, very steep very, very fast, and depending on the scale you're looking at it, it looks more or less vertical. This one I've tried to draw a little bit exaggerated, so if I were to draw a sequence of vertical lines on this thing, you will notice that it only ever crosses in one place at any given time. So since this maps exactly one input onto exactly one output, I can safely say that D is also a function. Now, one little hint for everybody that's watching the video through, anything that is one of the objects that you dealt with in Algebra 2, for example, linear equations and quadratic expressions, and later on you dealt with cubic expressions. Basically, anything that is a polynomial is automatically a function. So now that we've discussed how to determine if something is a function either from a set of ordered pairs or from a graph using our vertical line test, we do need to introduce some notation on how we deal with functions and kind of talk about why we would want to use functions in the first place. It kind of seems a little goofy because we've gone through most of Algebra 2 and Algebra 1 just talking about different features of graphs and not really thinking about what we would need to do if we wanted to transform one graph into something else. And that's where functions come in. Functions are very nice because it allows us to kind of shorthand some things. In other words, I only have to write it once if I can then just refer to that object as f of x from there on. So number one, it's nice because it allows me to shorthand some things. Number two, it's nice because it allows me to see what the input is going to be in a specific circumstance. So it's kind of another shorthand way of saying, I want you to plug this number in. And then the last thing that it allows me to do, which we get into a little bit later in the year, is it allows me to transform something that's kind of easy to deal with, like y equals to x, into something else that may be a little bit more difficult to deal with. So when we're dealing with functions, we have the notation f of x, and we usually say that it's equal to y, or in, I guess, more classrooms you'll see y is equal to f of x. Either way, doesn't much matter. This reads f of x equals y on that first line right there. So maybe I could color code that. This green dot right here goes with this green dot right here. And then this sort of pink dot right here goes with this pink dot right here. So that second line is y equals f of x. So f of x in this case, you'll notice that we've set it equal to y. They're both just sort of the same exact thing, like a statement that they're equal means that they're the same. So f of x is just another name for the dependent variable, or the output, at least in this context. So how do we use function notation? Function notation allows us to make a declaration, such as this in example 3, where I've said that f of x is a function equal to negative x squared minus 6x plus 4. And I've set a second function that I've called g of x, which is equal to 3x plus 1. And notice that I can vary the letter in front of it and include that little parentheses in x to make any function that I want. If I wanted to do, capital A of x, that it sometimes represents amounts in a bank account. I of x sometimes represents interest, that kind of thing. I can even vary what the input variable is. Sometimes you'll see t popping up throughout the course. But the point is that I can see what the name of the function is, and then I can see what the input variable is for that function. And that's one of the reasons why we like dealing with this function notation. Furthermore, what this allows us to do is that I can construct sets of instructions using this function notation. So problem A says, what is f of negative 3? Okay, well, f of negative 3 is basically a statement that is telling us to take the function f, which is this one, negative x squared minus 6x plus 4, and to plug in negative 3. And notice that if I had written that all out, I would have to write down take negative x squared minus 6x plus 4 again, and then I would have to say now plug in x equal to negative 3. Whereas f of negative 3 allows me to write several things very quickly, and then I can sort of shorthand it that way. It's kind of the first useful thing about function notation. So how does this work? What I'm going to do when I see function notation like this, and I've got a statement of what that function is, this says take the function named f and copy it down. So the function named f is this one, negative x squared minus 6x plus 4. And you'll notice that I copied this down in kind of a funny way. I've taken all of the x variables out because I'm going to replace them with this negative 3 right here. So now I'm going to plug in negative 3 into each of the parentheses, and I've got a nice number sentence from maybe about the 5th grade that I can evaluate at this point. So I've got, let's see, 9, negative 9 and positive 18 is positive 9 plus 4. This whole thing is going to end up being 13. It also allows me to plug other variables in. You'll notice on the second one it says f of r. So again, this says take the function named f and copy it down. But everywhere that I see an x, I'm going to take it out and leave a parentheses. Then I'm going to take the new input value that it wants, r, and I'm going to stick that in. And then I've got a nice number sentence that can be consolidated down. This is going to be negative r squared minus 6r plus 4. And you notice that all that had the effect of doing was replacing the x's in the original statement with r's. I can also do sort of complicated things with this. You'll notice that I have g of r plus 2 here. It means I can plug other things in that aren't just numbers or a single letter. I can plug more complicated expressions in that will in turn generate more complicated functions. So this says take the function named g, which is 3x plus 1, 3x plus 1. You notice that the same move happened here. I just took out the x and I left a parentheses. And then I'm going to plug in whatever it tells me to plug in here. It says what happens when you plug in r plus 2. And we have a nice easy number sentence here. We can distribute, combine, and simplify in this case. Since we are setting it equal to something we're not going to solve, we're going to combine it and simplify it. So I can send the 3 through the parentheses. That would give me 3r plus 6 plus 1. And then I notice that 6 plus 1 is just 7. And so, of course, I can come down here and write 3r plus 7. So g of r plus 2 is equal to 3r plus 7, and that is it. Okay, so I've cleaned up the board again. Kind of the last thing that function notation is very useful in doing is showing a graph whose equation I do not know. For example, I've got this green line here, but we don't have any rule like negative x squared plus something x plus something else to tell us what exactly that is. So what function notation gives us a way to do is it gives us another way to refer to an ordered pair. Sometimes you'll be asked to find what is f of 1 given a graph. This should be very simple once you get used to it. All it's telling you to do is go to where the input value is 1 on my graph, that's like right here, and find what the output value is. What is the y value? Well, if I do that, I'll notice that I have 1, 2 is the ordered pair there, and so f of 1 is just 2. In other words, what is the output value? Remember, that makes sense because f of x is just another way of referring to what the dependent variable is. What is y? So if I say, what is f of 1, it says, what is the output when I plug in 1? What is the output at 1? The y value at 1, 1, 2. And then give you a sequence of these things very quickly that you could find. So if I ask you for f of 0, of course we're going to go to where x is equal to 0, and I look for where the green line crosses. What is the output value? In that case, it is 3. Now you may be given some very funny looking graphs for this, but just note that all you're doing is you're reading an ordered pair off of the graph. It tells you what the x value is, and your job is to state what is the y value.